Hello everyone, hope all of you guys are doing well. So I am here to help you guys with your chapter 18 second set of homework. I think it's homework number 6 from chapter 16. Okay, so the first one. Choose the alternative that best completes the statement or answer the question. Hydrated aluminum ion. Aluminum hexahydrate is a weak acid in water. What are the products of its reaction with the water? How do you find the answer for this one? Now, this is a reaction where we talked about in our lectures that aluminum is a highly charged. It has a 3 plus charge on it, and it's a metal cation. So they can make hydrated cations in the presence of water. And then we also talked about these hydrated cations can further undergo an acid-base reaction like this. Let me show you where we talked about that with a diagram right here. Hydrated aluminum ion. You see here, this is the question that you have. Let's do slideshow from the current one so I can get my pointer. Okay, you see here, this is what you have. Aluminum in the presence of water can have a hydrated aluminum atom like this, aluminum 3 plus. Now when you put it into water, what's going to happen? See, oxygen is electron rich, aluminum is electron deficient, so the electrons would be pulled towards the aluminum ion. So as a result, hydrogen-oxygen bond can become more polar, and it could happen to any of these water molecules out of the 6. We are just showing you one molecule of water. So then if one of the bonds, hydrogen-oxygen bonds, get polar, another water molecule, oxygen atom of the water molecule, can come and grab that polar hydrogen away from the oxygen. Okay, from the polar bond. So as a result, so now this hydrogen oxygen bond will break and hydrogen will go to the oxygen and become H3O plus hydronium ion. Excuse me. So as a result, so now this oxygen has only one hydrogen. It becomes OH minus, right? Aluminum. Now it has 1, 2, 3, 4, 5 water molecules and OH 2 plus, because aluminum was 3 plus. Now with OH minus 1 plus 3 and minus 1 will make it plus 2. So the overall charge of the molecule or the complex is going to be aluminum with 5 water molecules and OH with 2 plus and hydronium ion. So the first question talks about this concept over here. So with that in mind, you can answer the correct answer here. Okay, choose the one that represent that products that I have just showed you. Okay, 5 water molecules with aluminum, OH2 plus and hydronium ion. And I see that answer here. So you guys pick which one is the correct one. Alright, okay, the next one. Select the pair of substances in the acid is listed followed by its conjugate base. First thing is the acid and then it has to be the conjugate base. So remember, what is an acid? Acid is, Arrhenius concept of acid is something that you can donate a hydrogen or a proton. So going from acid to base, you should see a removal of a proton or a loss of a proton from acid to the base. Now with that in mind, if we look at the first one, HPO4 minus 2, and you have H2PO4 minus 1. We have to look at the acid and the conjugate base. Now, if you look at HPO4 2, how many hydrogens are there? 1 hydrogen. There are 2 hydrogens here. So, has the hydrogen lost or gained? Increase, right? The number increase. So, can it be acid and the conjugate base? No, right? Because the number of hydrogen had increased. So acid and base combination should be, acid should have one hydrogen more than your conjugate base. Now let's look at ammonia. Has how many hydrogens? 3. And NH4 plus ammonium ion has 4 hydrogens. Again the number of hydrogen increased. Can it be your conjugate acid base pair? No, right? So then you have a hydrogen carbonate. One hydrogen, there's nothing here. So hydrogen has lost. So that you can consider conjugate acid is hydrogen carbonate, and then the base is carbonate -2, because now it has lost with the negative charge, and losing another proton will make it -2 charge. And then let's look at the other ones too. Proton, H plus HCl. Same number of hydrogen, so we cannot consider that as a conjugate acid base pair. And then the next one, acetic acid. These hydrogens on carbon, they are not ionizable hydrogens. They are not going to define your molecule as an acid. Only this hydrogen next to the oxygen will be the only one that could consider as ionizable hydrogen. And then this one right here has taken another hydrogen. So 1 and 2 number of hydrogen had increased. Again, that cannot be considered as conjugate acid base pair. Okay, so go with the one that you have more hydrogens to begin with, one more hydrogen to begin with than the product. Okay. Okay, so the next one. Again, it has to be just one hydrogen difference. Number 3, select the pair of substance that is not a conjugate acid base pair. Now, with the same concept that we have talked about, you should be able to answer this question as well. Again, it's asking acid base. So we have to first choose the acid, then the base. 2 hydrogens here, 1 hydrogen here. We are asking for not a conjugate acid base pair. So A, does it look like it's a conjugate acid base pair? It does, right? There are 2 hydrogens to begin with, 1 hydrogen, HSO4. And then this one here, you have 2 hydrogens, and then here you have 0 hydrogen. So what do you think about that? Well, it has to be only 1 hydrogen difference. So if you take H2S, when you lose a hydrogen, so this is H2S, it should be HS minus, has to be the conjugate base, not S2 minus, because it has to be 1 hydrogen different. So B doesn't look correct. Let's look at the C. 3 hydrogens, 2 hydrogens. Well, that could be a conjugate acid base pair. 1 hydrogen, no hydrogen. That's fine too. Here you have 3 hydrogens, 2 hydrogens. Right. So the one that is not a conjugate acid base pair then going to be H2S and S2 minus, because 2 hydrogens had lost. Okay. And HS minus can become conjugate acid base pair S minus 2 like this. These 2 will be, but not these 2. Okay. It has to be 1 hydrogen difference. Number 4, the acid dissociation constant Ka equals 1.26 into 10 to the negative 2 for hydrogen sulfate anion and 5.6 into 10 to the negative 10 for ammonia. Which statement about the following equilibrium is correct? And we are given an equation. We have HSO4 minus with ammonia NH3 giving you sulfate anion and ammonium ion. Okay, now we can figure out by looking at this equation which one is the acid, which one is the base. Now hydrogen sulfate, HSO4 minus, sulfate here, meaning HSO4 minus is your acid and the conjugate base is sulfate anion, conjugate base for the hydrogen sulfate acid. And ammonia is the base, and then ammonium ion is the conjugate acid for that ammonia molecule. Okay, so we are given Ka values, acid dissociation constants for the acid. So HSO4 we are given, and ammonium ion NH4, this one also given. So this is this value and this is this value. Now which one is a strong acid between these two? Strong acid would be the one that has a higher Ka value, acid dissociation constant. HSO4 minus 1.26 into 10 to the negative 2. 5.6 into 10 to the negative 10 is for the ammonium ion. So which one is a strong acid from these two then? The one which is higher Ka. So sulfate, hydrogen sulfate is the strong acid. Remember what we said regarding how the acid and bases work? Whether it is going for the forward reaction or the reverse reaction will depend on which side we have the strong acid and the strong base. Always strong acid react with a strong base to give you weak acid and weak base. So we have our strong acid on the left side and we have our weak acid on the right hand side. Now since the numbers are not given, we don't know about the base's strength, but it's okay. With the given data, by only looking at the acid, we should be able to figure out which direction the reaction proceeds and which ones are the strong acids and the bases. So now according to the Ka given, which direction do you think this reaction would proceed? Is it going to go to the right or to the left? Right, right? Yes, it's going to go towards the right side because we have a strong acid in our left side, which is HSO4 minus. So with that in mind, let's see what are the choices given to us. Neither reactants nor products will be favored because all of the species are weak acids and bases. No, that's not true. The reactants will be favored, meaning this side would be favored because ammonia is a strong base than the sulfate. Ammonia is a strong base, talking about this one. If it is a strong base, then it has to go to the right side, meaning the product side. So the B is not correct, right? C, the products will be favored because hydrogen sulfate ion is a stronger acid than ammonium ion. Isn't that correct? That's correct, right? HSO4 hydrogen sulfate is a stronger acid than the ammonium ion. We just looked at it, looking at their Ka values. So C, correct. Let's look at D also. The initial concentration of the hydrogen sulfate ion and ammonia must be known before any prediction can be made. No, that's not correct. We don't need those information. This reaction is impossible to predict since the strong acid and the weak base appear on the same side of the equation. No, that's not correct either. So we have a right answer. We just talked about it, right? Okay. The next one, 5. Aqueous solution of phosphoric acid and sodium nitrite are combined and the following equilibrium is established. And the equilibrium constant Kc for this reaction is greater than 1. If the equilibrium constant Kc greater than 1, what does that mean? That means it will move, giving you products moving to the forward direction. If the Kc for the reaction is greater than 1, meaning reaction would proceed to give you products. If it is less than 1, then it would proceed to give you more of your reactants. Okay, so that information you should know. We talked about this in our lecture videos. Okay, now with that in mind, let's see. Dihydrogen phosphate anion is a strong acid than nitrous acid. Okay, so once you figure out that the reaction will proceed making more of the products, one conclusion that you can come up is the acid and the base that you have in your left side is going to be a strong acid and strong base. Because remember always, strong acid and strong base react to give you weak acid and the weak base. So again, you need to figure out between the reactants, which one is the acid, which one is the base. Remember, the way you find out your acid is, your acid, you will see one hydrogen less in the product side. For the base, you will see hydrogen has been added to the base on the left side when you go to the right side. So H3PO4, what do you think that? Is it going to be acid or base? So the conjugate acid-base pair for this is going to be H3PO4 and H2PO4. So 3 hydrogens will become 2, meaning this is your acid. And the conjugate base for that acid is this one. So then the next one, nitrite, NO2, going to be your base, and the conjugate acid for that is HNO2, right? And always, since it says that the Kc greater than 1, H3PO4 is going to be a strong acid, NO2 going to be your strong base. What you have in the right side going to be your weak base and weak acid. Okay, excuse me. The dihydrogen phosphate anion is a stronger acid than nitrous acid. Now dihydrogen phosphate is this guy over here. There are 2 hydrogen. Dihydrogen phosphate anion is a strong acid than nitrous acid, HNO2. What do you think about that? Is that true? No, right? That is not true. Because your nitrous acid HNO2 is an acid, and in the according to this equation, your dihydrogen phosphate is a base, and which is the weak base. Okay. And then B, phosphoric acid is a weaker acid than nitrous acid. Is that true? Phosphoric acid is an acid right here, H3PO4. And then the nitrous acid is this one over here. Now, if the Kc is greater than 1 between the two, which one is a strong acid? It is a phosphoric acid, is a strong acid. So B is not correct either. The nitrite anion is a weaker base than the dihydrogen phosphate anion. Dihydrogen nitrite is this one right here. Dihydrogen phosphate is this one right here. Is it doing anything? This is your dihydrogen phosphate. This is your nitrite. And nitrite anion is a weaker base than the dihydrogen phosphate anion. That's not right either, right? Because if the reaction is moving to give you products, then the nitrite is a stronger base. Okay. Nitrous acid is a weaker acid than water. Well, water is not given here, so we're not going to talk about that. And then the phosphoric acid, for D, nitrous acid is a weak acid than water. Since the pKa values or the Ka values are not given, you cannot compare it right here. Phosphoric acid is a stronger acid than nitrous acid. Great. So phosphoric acid here, stronger acid. And your nitrous acid is right there, weaker acid. Always strong acid and strong base give you weak acid and the weak base. So the nitrous acid is going to be your weak acid. So phosphoric acid is a strong acid. So right there we have an answer for you. Okay, great. Number 6. Excuse me. Butyric acid is responsible for the odor in rancid butter. A solution of 0.25 molar butyric acid has a pH of 2.71. What is the Ka for the acid? Okay. Now, it is asking about the Ka, butyric acid. You may have not heard about butyric acid name before. But since the Ka value is given, then you should know that it is a weak acid. Okay, remember we don't have Ka values for the strong acid, so it's a weak acid. And you don't need to know the structure of butyric acid. We can just consider it as Ba. Okay, so how do we approach this one? We want to find out the Ka. The first thing is you're going to write down the equation of a weak acid, how it react in water. Let's consider our butyric acid as HBA. H is the ionizable hydrogen, butyric acid, right? Plus water. So what happened when you add an weak acid to water? Water, lone pair of oxygen, goes and grab this hydrogen, right? And then it will become H3O plus. H2O will become H3O plus. So the BA, butyric acetate, not butyric acid, butyrate will become your anion Ba minus. Okay, so that is how any weak acid will react in water. You always write down the hydronium ion and the anion of the acid, right? And we are given butyric acid has a pH of 2.71. We want to find out the Ka for the acid. And then the next thing is you're going to set up your ice table. Initially, we are given, excuse me dear, 0.25 molar. 0.25 molar. And then water, we have plenty of water. Don't worry about the water. And the hydronium, nothing. Butyrate, nothing. And then the change we can consider X. So, and at the end, change would be 0.25 minus X, right? Okay, so you write down your ice table. We want to find out the Ka. And Ka is hydronium ion concentration times Ba over HBa, right? And we are given pH 2.71. So pH is the negative log of hydronium ions. Remember, pH equals negative log of H3O plus. Now, how does we get the pH? Based on the hydronium ion concentration. What hydronium ion concentration are we talking about? It is this hydronium ions, which is given due to the dissociation of your weak acid. So we are given pH as 2.71, meaning if you can find out the hydronium ion using this pH, that will give us this X amount, right? So then the hydronium H3O plus would be 10. We have to take the inverse log of 2.71 hydronium ion concentration. Okay, so when you do this calculation, you put this number into your calculator and let me know what number you get, please. All of you guys go ahead and put this number to your calculator. Shift log 2.71 negative. That would be, I might get a wrong number, so you will have to check to see if you get the correct number. 1.95 into 10 to the negative 3. And that is hydronium ion concentration. In other words, we just found out the X, right? So that is also your X. X equals 1.95 into 10 to the negative 3, right? Now we want to find out Ka. So then your Ka going to be H3O plus times Ba minus over HBa, right? So this is what I did. Your hydronium ions times Ba minus over HBa, okay? And here we are going to make an assumption. Now what we are going to use is the equilibrium amounts, right? So hydronium ions were all X and Ba minus also X. So that was X squared. I mean, it's hard to say X squared, right? It's a tongue twister. Over HBa. Excuse me, dear. HBa equilibrium is 0.25 minus X. And here we are going to make an assumption. X is small. 0.25 minus X is almost as 0.25, right? So you put that 0.25 here. 0.25, right? We found x, this value. So then your Ka going to be 1.95 into 10 to the negative 3 raised to the power 2. Remember, it has to be x squared, and then you divide by 0.25. That will give you Ka. That's how you find the Ka. Okay, do that calculation and tell me what number you get for your Ka. We are doing question number 6. What number did you get? So, something like 1.5 into 10 to the negative 5, right? Very good. So, that's going to be your answer. And remember, now we have used here an assumption. 0.25 minus x is similar to 0.25. So we can check to see if our assumption is correct. To that, we're going to look at the percentage of dissociation. Percentage of dissociation, which is x amount over initial concentration times 100. So that's how you find your percent dissociation, as well as to see if our assumption is justified, right? So what is the x amount that we got? Remember, we calculated x to be 1.95 into 10 to the negative 3, and you divide it by initial concentration 0.25 times 100. So this is the way that you justify your assumption. So when you do this one, what would you get? Can you do this calculation and tell me what you get? It should be 0.78, something like that. So 0.78%. So if this is less than 5%, assumption is justified. If it is greater than 5%, then we cannot use 0.25 minus x equals 0.25. So you have to use 0.25 minus x, right? So our assumption is justified, and we also found the Ka. Okay? All right then. We will stop this session here, and I will start the rest in a different video. So what we just now did is 6.